Actually, having looked at this question again and the threads that it has generated, I realized that I was overly pessimistic. 7 and 21 both are impossible, and this has both been proved. What has happened is that the original poster both has already proved that 7 is impossible. Then the answer, Gordon Royal conjectured that 21 is also impossible, and actually both proved this in the comments. So we know a little bit more than I thought we did. So 7 and 21 are impossible. All other numbers up to 8555 are possible. We don't know about higher numbers. But so much for Hamiltonian paths. The next natural question, of course, is Hamiltonian cycles. What about those? So by the easy-reday theorem, every tournament has a Hamiltonian path. But of course, not every tournament has a Hamiltonian cycle. Why? For example, this one, you cannot go, every arc goes from a smaller vertex to a larger one, but a cycle would at some point have to go down, and that's impossible. So one abstraction is clear, namely, if a digraph D has a Hamiltonian cycle, then D is strongly connected. Remember, this means that you have at least one vertex, and from any vertex to any vertex, there is a path. Why? Because if you have a hemp, then you can go from any vertex to any vertex just by following the hemp. It's like a train that goes, it's like a train that supports every station. Of course, in general, this is only a necessary criterion for a hemp. For a hemp, not a sufficient one. However, it turns out that for tournaments, it's also sufficient. So, in other words, if a tournament D is strongly connected, then D has a hemp. And we have to be a little bit more careful. We have to require that it has at least two vertices, because a single vertex does not a cycle make unless there is a loop, but we don't have loops. This is known as Kemion's theorem. And I will not go into the details of the proof because it's in the notes, it's in various books as well. But this is a nice proof to show on the blackboard. And I think I have something like a blackboard here, which is an editor for commutative diagrams that I'm abusing to do this. So how do you prove that there is a hemp? Here is one way. You pick a maximum length cycle and you argue that that cycle must be a hemp. Assume the contrary, so it's not a hemp. So you have this maximum length cycle, but because it's not a hemp, it has to miss at least one vertex. So there is one vertex W not on the cycle. And because you have a tournament, this vertex W must be joined by an arc with each of the vertices of the cycle. You just don't know whether it's whether the arc is directed to W or from W. But let's start somewhere. Let's assume that there is an arc from W to V0. We'll talk about the other case later. And I'm already seeing I mislabeled the vertices. If one of them is V0, the next should be V1, of course. So what do you know about VK and W? Well, there is either an arc from W to VK or an arc from VK to W. However, I claim that the latter case cannot happen, because if there is an arc from VK to W, then you can make the cycle longer. Namely, you go V0, V1, V2, ... VK, but then instead of going to V0, you take the detour through W. So you get a longer cycle, and that's a no-no because it was already the longest cycle. So you cannot have an arc from VK to W, so you have to have an arc the other way around because it's a tournament. Next, you look at the previous vertex, so vk minus 1. And you do the same argument. If there was an arc from Z to W, you could use it to lengthen the cycle, but because the cycle is already maximum length, that's impossible. So we have an arc here. And by induction, you show that there is an arc from W to every vertex of the cycle. Now, that was only one case. In the other case, you have an arc instead of from W to V0, you have an arc from V0 to W. What about that case? Unfortunately, I've undone the corrections now, but fine. So if you have an arc here, well, you can make a very similar argument then to show that you have an arc here, and so on. So what we know is that every vertex that's not in the cycle, it either has arcs from all vertices on the cycle, or it has arcs to all vertices on the cycle, but this is the only option. So let's call this a two vertex, and the previous case we call it a from vertex. So maybe we should put a from vertex somewhere here just to have both cases illustrated. The diagram is of course getting a little bit messy. Maybe I should have taken a smaller cycle. Now, however, so of course, these vertices cannot be the same. It's either from or to. So if you have a from vertex and a to vertex, now you have to look at how would you get from the to vertex to the from vertex. Because the digraph is strongly connected, you have to be able to get somehow from one to the other. And the thing is, if you move away from a to vertex, you cannot get to the cycle. So you can only get to either another to vertex or to a from vertex. So there must be an arc that goes from a to vertex to a from vertex, right? Otherwise, you just couldn't get from one type to the other. You couldn't get from a to vertex to a from vertex. You can't get to it through the cycle. So you have to get to it directly somehow. And now, okay, so I need a delete button. I'm gonna delete everything but just one arc. Not sure how to do this. So. Okay, I ended up deleting the wrong arc. Okay, so now, however, you still have a contradiction because you can still lengthen the cycle. It's just a little bit more complicated. You started with 0, you go all the way down to Vk, then you go to W, then you go to U, and then you go to V0. So you've lengthened the cycle by 2 arcs, not by 1. Okay, so the only way this argument would fail is if there are no to vertices or no from vertices. But this is again impossible because you cannot get from a to vertex to the cycle. So you cannot get it directly. So you have to be able to go through a to vertex. Through a from vertex. So it's easy to basically get rid of all the possibilities, and then you realize that nothing is actually possible. The only possibility is that the cycle already has all the vertices in it. So there is neither from vertices nor to vertices. And in this case, it's a Hamiltonian cycle, QED. So much for the proof. And there is a few more things to say. You can try to bound the numbers of Hemks and the numbers of Hemps, but I will leave it at that.